You know, when you look at one of those classic optical illusions, like that famous line drawing that is either a duck or a rabbit.
Oh yeah, the duck rabbit, a classic.
Right. So your brain has this inherent, I guess, almost desperate expectation of being able to see the whole picture at once, you know?
Yeah, you want to grasp the total reality of the image on the page.
Exactly. But you can't. You look one way, the lines form a duck's beak. Then you blink or you like shift your focus slightly, and suddenly those exact same lines are rabbit ears.
And you can never truly see both animals simultaneously. It's totally binary.
It is, and it's incredibly frustrating when you sit down and really think about the limitations of your own perception. I mean,
Because your perception is basically forced to choose a framework. It is either one reality or the other.
right, there's no duck-rabbit hybrid image your brain can process. Your mind just sort of violently jumps between the two interpretations depending on what specific details you choose to focus on.
Yeah, and we find it comforting to just pick one, you know?
Yeah.
Say, okay, for all intents and purposes, right now, this is a duck.
Yes. We like our reality to be singular. We like our frameworks clean and, non-contradictory. But, and this is where we're going today, then you step into the world of foundational theoretical physics.
Where things are anything but clean.
Exactly. Specifically, the attempts to understand the very fabric of the universe. Because when you look at the macro universe and the micro universe, we're basically staring at the ultimate cosmic duck-rabbit illusion.
That's a great way to put it. The structural landscape of modern physics is deeply divided. It is the absolute definition of theoretical muddy waters.
Which is wild to think about.
It is arguably the most profound division in all of human knowledge right now. I mean, we have built two phenomenal, incredibly accurate lenses through which to view reality, and they simply refuse to overlap.
So welcome to this deep dive. If you're joining us, it means you have that itch. You want to get to the bottom of incredibly complex ideas, but you do not want to be buried under a mountain of incomprehensible academic jargon.
We're going to try our best to avoid the jargon today.
We really are. Our mission today is to unpack a foundational scientific paper that attempts to tackle this exact divide we're talking about. We are looking at a proposed framework called the Osmakani model.
And along with that, something known as the Mulham Equation.
Right. And the stakes here, they are astronomical. We are not just talking about tweaking an existing rule of physics. This is an exploratory framework attempting to completely reformulate the very relationship between mass, space, and time.
But we should probably set expectations early, though.
Oh, for sure.
Because the paper itself adopts a very cautious, intellectually honest tone, and we need to mirror that.
Right, they aren't saying they've solved everything.
Exactly. The Osmakani model is not claiming to be a finished product that you can take to an engineering lab today. It does not claim to completely replace our current working theories right now.
Okay.
Instead, it is proposing a unified relational structure. Think of it as an exploratory foundation meant to evolve into more complete relativistic and quantum theories later on.
Mm.
It's an attempt to lay an entirely new kind of cornerstone.
Okay, let's unpack this. Because before we can appreciate how the Osmakani model works, we have to understand why anyone felt the need to invent it in the first place.
You have to know the problem to appreciate the solution.
Exactly. We have to establish the stakes. The paper immediately points to a foundational problem. So walk me through the history of this great divide in modern physics. Why are we stuck with two different frameworks?
Well, the foundational problem is the conflict between the macro world and the micro world. So let's start with the macro.
Okay, the big stuff.
Right. On one side, you have general relativity. This is Einstein's masterpiece from 1915. It deals with the massive stuffed stars, galaxies, black holes, the overall structure of the universe.
Got it.
In general relativity, gravity isn't a pulling force like a magnet. It is the geometric curvature of space-time itself, generated by mass and energy.
Okay, so this is the classic trampoline analogy, right?
Exactly. Imagine space-time as a smooth, continuous trampoline. If you place a heavy bowling ball on it, representing a star, it creates a curve, a depression in the fabric. Other objects roll toward it because of that curve.
That makes sense.
That smooth geometry is the macro world.
I'm visualizing the trampoline, smooth, continuous, and highly predictable. Like, if I know the mass of the bowling ball and where it is, I know exactly how the trampoline curves, and I can calculate exactly how a marble will roll around it.
Yeah, that is the beauty of general relativity.
Yeah.
It is deterministic and it's continuous. But
Yeah.
then you zoom in.
How far in?
Way, way in, past the planets, past the molecules, down to the level of individual atoms, electrons, photons. And suddenly the trampoline just vanishes.
Yeah, it's just gone.
The smooth geometry completely breaks down. Now you are in the micro world, and the rules are dictated by quantum mechanics. And quantum mechanics does not care about smooth curves.
Okay.
It relies on probabilities, wave functions, and fundamentally, quantization.
Okay, let's stop and define quantization for the listener, because that is a term that gets thrown around in sci-fi a lot, but rarely ever explained.
Yeah, people love throwing that word around.
Right, so when you say quantization, you mean reality stops being a smooth gradient and becomes chunky, right?
Chunky is a really good word for it. In the quantum world, energy and matter don't flow continuously. They exist in discrete jumping packets, or quanta.
Okay.
Think of walking up a ramp versus walking up a flight of stairs. General relativity is the ramp. It's smooth and continuous. You can stand at literally any microscopic point on the ramp.
Right.
But quantum mechanics is the staircase. You can stand on step 1 or you can stand on step 2, but you physically cannot stand on step 1.5. You have to jump from one allowed energy state to the next.
Oh, wow. So reality suddenly becomes pixelated when you look closely enough.
That is exactly the paradox. General relativity is analog. Quantum mechanics is digital. And here is the massive blind spot that has haunted physicists for a century. Despite the enormous experimental success of both frameworks in their own domains, they do not play well together.
They don't mix at all.
Not at all. When you try to use the math of general relativity in the quantum world, the equations spit out infinite nonsensical answers. The math literally breaks down.
Yikes.
And conversely, when you try to apply quantum mechanics to the curvature of the cosmos, it just doesn't work.
Wait, hang on. I'm struggling with that. Why can't we just leave them separate? Like, why can't we just say, okay, the ramp works for big things, the stairs work for small things. Let's just use the right tool for the right job.
Because the universe doesn't have a dividing line. The universe is one single entity. A star, which requires general relativity to understand, is entirely composed of atoms, which require quantum mechanics to understand.
Oh, right. Obviously.
Furthermore, there are extreme environments in the universe where both frameworks absolutely must apply simultaneously. Think about the center of a black hole, or the very moment of the Big Bang.
Where you have super heavy and super small at the same time.
Exactly. You have an enormous amount of mass requiring general relativity crushed down into an infinitesimally small quantum space requiring quantum mechanics. When physicists try to calculate what happens there, the two theories violently contradict each other. We get mathematical gibberish.
It's like, okay, it's like we have two incredibly accurate, highly detailed maps of a single city. But one is a subway map showing all the underground, pixelated jumping routes between specific stations. That's quantum mechanics.
I like that.
Right. And the other map is a beautiful satellite view of the smooth, continuous streets above ground. That's general relativity. And we are standing here holding both maps, completely lost because no one can figure out where the stairs are to connect the underground to the surface.
That's a perfect analogy.
Yeah.
We literally cannot find the stairs, and we spent decades trying. Theories like string theory or loop quantum gravity have attempted to build those stairs, but they often require, unobservable extra dimensions or incredibly convoluted math that we just can't test yet.
Right, gets super abstract really fast.
Yeah. And the paper we are discussing today highlights this exact missing link. We do not fully understand the deeper relationship between quantization, those digital jumps in mass, orbital structures, and the geometric curvature of spacetime. We have a massive conceptual void.
Which brings us to the Osmakani model. So if this model is attempting to build that bridge, how does it start? Because to connect the subway map to the street map, you have to fundamentally realize they're describing the same physical space. How does this paper tackle the problem?
It tackles it by forcing a massive philosophical shift regarding the three most basic ingredients of reality, mass, space, and time.
Okay.
The central hypothesis of the paper states that mass, space, and time are not fully independent entities, but rather interconnected components within a universal dynamic relative equilibrium.
Okay, let me stop you there because that sounds really elegant, but we need to put it to the test and visualize it.
Yeah.
Because normally my understanding of physics is that space is an empty room, just a void. Time is just a ticking clock on the wall of that room, ticking away at a constant rate. And mass is just the furniture we place inside the room.
Right.
They are totally separate things. I can move the couch without changing the clock or altering the dimensions of the walls.
That is the classical Newtonian way of thinking. The void, the absolute clock, and the isolated matter.
Yeah.
Einstein challenged this by showing mass can curve the room and slow down the clock, but the Osmakani model pushes it to an absolute extreme.
I'll say.
It asks you to throw the empty room image away completely. It proposes that mass, space, and time are all building blocks woven out of the exact same relational fabric.
Wait, really?
Yes, you cannot change the mass of the furniture without instantaneously and fundamentally altering the geometry of the room and the ticking of the clock in that specific physical system.
That is wild.
They generate motion, stability, and even quantization together as a single package deal.
So the room, the clock, and the couch don't exist independently at all. They only exist in relation to one another.
Yes. The universe isn't a container holding objects. It is a web of relationships. And these relationships are governed by what the model calls a triple relative equilibrium.
Triple relative equilibrium.
Yeah. To formalize this, the paper introduces a foundational equation. This is the structural core of the entire model.
Now, I know doing math on an audio deep dive can lose people really quickly, so let's break it down slowly. Walk us through this triple equilibrium equation, and let's focus on what the ratios actually mean rather than just, like, reciting the formula.
Okay, I can do that. The equation basically multiplies three different ratios together, and the result must always perfectly equal to number 1.
Okay, equal to 1. Got it.
First, you take the ratio of two interacting masses in a system, say, an electron and a nucleus. So
Yeah.
mass 2 divided by mass 1.
Right.
Next, you multiply that by the square of the ratio of their orbital times. So time 2 divided by time 1 squared.
Mass ratio times time ratio squared.
Exactly. And finally, you multiply all of that by the cube of the ratio of their spatial dimensions, or their orbital radii.
Yeah.
Space 1 divided by space 2 cubed.
Okay.
Multiply the mass ratio, the time ratio squared, and the spatial ratio cubed, and it equals exactly 1.
Okay, so mass 2 over mass 1 times time 2 over time 1 squared times space 1 over space 2 cubed equals 1. Let me try an analogy to stress test this.
Let's hear it.
I am visualizing this like an intricate, incredibly delicate, cosmic hanging mobile, like the kind you hang over a baby's crib but made of galaxies and atoms.
Oh, nice.
In this mobile, everything is perfectly balanced. If I reach up and swap out one of the ornaments for a heavier one, so I change the mass ratio, the whole thing is going to tip over and fall apart.
It would, yes.
Unless I simultaneously shorten the length of the string, which is the spatial ratio, or I change how fast the mobile is spinning, which is the time ratio. The equation says I have to adjust all three properties in tandem to keep the entire system balanced at exactly the number 1.
That analogy holds up incredibly well, actually. If you perturb the mass, the space and time must compensate to maintain that equilibrium. But let's take your mobile analogy a step further to answer one of the biggest mysteries we just talked about, quantization.
Okay, the staircase.
Remember the staircase?
Yeah.
The idea that energy comes in digital chunky jumps and we don't fully know why.
Yes, the pixelated subway map.
Right. So in conventional quantum mechanics, we largely accept that things are quantized just because experiments tell us they are. It's treated as a fundamental rule imposed on nature. But under the Osmakani model, quantization is not an arbitrary rule.
What is it then?
It is an emergent consequence of this triple relative equilibrium.
Wait, I'm struggling to see how balancing a mobile creates a quantum jump. How does that leap happen?
Think about the math of the equation we just went over. Mass, time squared, space cubed. These are highly specific, constrained mathematical relationships, right?
It's very rigid.
So the system can only find a stable, balanced state. It can only keep the mobile from falling apart at very specific, discrete mathematical intervals. If an electron tries to orbit at a spatial radius that doesn't perfectly balance the mass and time ratios to equal exactly 1, the relationship is unstable. It collapses.
Oh.
Therefore, the electron can only exist at the specific spatial radii that satisfy the equilibrium. Those stable, balanced states are the quanta.
Oh my gosh, that is completely counterintuitive, but it makes so much sense.
Right.
It removes the mystery of the rule and replaces it with a mechanical structural necessity. Things are quantized, things jump between stairs because the space between the stairs is mathematically unstable. The mobile falls apart if you try to stand on step 1.5.
Precisely. It is a profound philosophical shift from quantization is a law of nature to quantization is the only way the relational structure survives. It is an emergent property.
Wow. So if we have this new framework, this unified relational thread tying mass, space, and time together, how do we actually measure the strength of that thread?
That requires a constant.
Right, because every major physics framework has its signature constants. You cannot talk about relativity without the speed of light. You cannot talk about quantum mechanics without Planck's constant. So what anchors the Osmakani model?
To anchor this framework, the paper introduces a brand new fundamental coupling constant. It is denoted as Gym.
Okay, let's talk about Jim. Because I looked at the paper before we recorded, and this part totally threw me for a loop.
I'm not surprised.
The physical dimensions for this new constant, how it is measured in physics, are meters cubed per kilogram second squared. Those are the exact same units of measurement as Newton's gravitational constant, big G, the thing that explains why apples fall from trees.
They're the exact same units. But within this model, Gym is absolutely not a Newtonian gravitational constant.
Well, I figured it couldn't be, because the value the paper assigns to Jim is absurd.
It's quite large, yes.
Large. Newton's G is an incredibly tiny number. It's roughly 6.67 times 10 to the negative 11th. It's the reason why gravity is actually considered a very weak force, right? It takes the mass of an entire planet just to hold a feather to the ground.
Correct.
But this new Gym in the paper, the value provided is approximately 1.5142 times 10 to the 29th.
Yes.
That is a 1 followed by 29 zeros. That is incomprehensibly huge. If a force that strong is operating at the atomic level, why doesn't it just crush every atom in the universe into a black hole?
That is exactly the question you should be asking. Because if Gym were a vector force pulling things together like gravity, we would be crushed instantly. Yeah. But it is not a pulling force.
Then what is it?
Gym is a universal relational coupling constant, the fundamental glue of the structural framework. Think of it not as a force pulling objects together, but as a metric of the stiffness or the structural integrity of the space-time mass relationship itself. Its immense size reflects how incredibly rigid and strong the underlying relational fabric must be to maintain stability at the quantum level long before those relationships manifest as the weak macrogravity we feel.
Okay, so it's not gravity pulling a planet. It's the underlying structural tension that allows mass, space, and time to exist as a unified fabric in the first place.
You've got it.
So if we have this massive new structural glue, where does it actually fit? What equation puts Gym to work to build the bridge between the micro and the macro?
This brings us to the core postulate of the paper, the Mulham Equation. It is a deceptively simple formula that connects the absolute foundations of physics. The equation is Gm multiplied by mm squared equals h bar multiplied by c.
Okay, Gm times mm squared equals h bar times c. Let's break this down variable by variable, starting with the right side of the equation. We have h bar times c.
Let's look deeply at h bar first, the reduced Planck constant. To a layperson, it's just a tiny number. But physically, it represents the fundamental graininess of the universe.
The graininess.
Yeah, it dictates the minimum possible amount of action or angular momentum in the quantum world. It is the size of the pixels on the subway map we talked about. That is the absolute bedrock of quantum mechanics. Then you multiply it by c, the speed of light.
And the speed of light isn't just about how fast a flashlight beam travels. It's the ultimate speed limit of causality in the universe. It's the bedrock of relativity.
Exactly.
So the right side of the Mulham equation is literally the foundational constant of quantum mechanics multiplied by the foundational constant of relativity.
Which is huge. You are fusing the pixel size of the micro world with the causality limit of the macro world.
Incredible.
Now, look at the left side of the equation. You have Gym, our massive new Osmakani relational constant, our structural glue, and it is multiplied by m squared. M is a brand new concept introduced here called the Mulham reference mass.
And here's where it gets really interesting for anyone who remembers basic algebra. You can rearrange this equation to solve for sol phi.
Yes, you can.
The Mulham mass is just the square root of the right side divided by the left side. It's the square root of h bar times c over Gem.
Look at the profound implication of that rearrangement, though. The paper isn't just inventing a mass out of nowhere. It is defining a natural, fundamental unit of mass entirely out of universal constants.
Wow.
It is forging a physical mass out of the quantum graininess, the relativistic speed limit, and the structural tension of the universe. It's a bridge built entirely out of the constants that govern reality.
It's essentially saying that mass itself isn't just a random property of matter, right? It's a structural necessity born out of the relationship between quantum action and the speed of light.
Precisely.
And the paper doesn't stop at mass, does it? I saw something about a length as well.
Correct. From this exact same set of constants, the paper derives the Mulham length, denoted as m.
What does that do?
Well, in conventional physics, you have the Planck length,
Mm,
which is generally considered the smallest measurable distance before our current understanding of physics totally breaks down into quantum foam.
right.
The Mulham length serves a similar foundational purpose, but specifically for the Osmakani relational structure. It provides the baseline geometric grid for the universe. It defines the smallest possible unit of relational space.
Okay, let's step back and look at the whole board here. We have these grand, sweeping theoretical concepts. We have the unified thread of mass, space, and time. We have an underlying structural tension, a foundational mass, and a baseline grid for space.
It's a lot to take in.
It is. But I need to put this to the test. How does any of this abstract math actually apply to the real world? How does it apply to, like, the electrons buzzing around the atoms in this microphone?
That's the real test.
Yeah.
A theory is only as good as its ability to map onto reality. The paper must prove that these abstract constants govern actual particles. And to do this, it introduces the dimensionless Osmakani coupling constant.
Okay, let's clarify dimensionless for a second. We just talked about constants having units, like meters per second or kilograms. Dimensionless means it's just a pure number, right? No units attached.
Right. A dimensionless constant is pure ratio. It describes the pure strength of the relationship between any two particles, independent of the measuring system you use.
So it's universal.
Exactly. The equation for this coupling strength, denoted as alpha O, is gem multiplied by mass 1 multiplied by mass 2, all divided by h bar times c.
Okay, so you take the mass of your two specific particles, you multiply them by the massive structural glue, Jim, and you divide it all by the quantum and relativity constants.
Yep.
And the result is a number that represents how strongly those two specific particles are coupled together in this relational framework.
Yes. And this is where the paper delivers its most mathematically compelling argument.
Ooh, okay.
The authors decide to test this coupling equation on the most fundamental relationship in all of chemistry and atomic physics, a single proton and a single electron, the classic hydrogen atom structure.
Okay, the absolute basics. What happens when they run the math?
They plug the known measured mass of a proton in for mass 1. They plug the known mass of an electron in for mass 2. They apply the equation. And the value that tops out for the proton-electron coupling is approximately 7.297 times 10 to the negative third.
I'm going to stop you right there because to a casual listener, 7.297 times 10 to the negative third just sounds like a random tiny string of numbers, 0.007297. Why should anyone care about that specific decimal?
Because anyone who has studied quantum electrodynamics will instantly get chills looking at that number.
Really?
Yes. It is astonishingly close to one of the most famous, most mysterious numbers in all of science, the fine structure constant.
Okay, let's do a deep dive on the fine structure constant for a minute because understanding why it's a big deal is crucial.
It really is.
In standard physics, the fine structure constant, which is often approximated as 1 over 137, is basically a magic number. It dictates the strength of the electromagnetic interaction. It determines how strongly light interacts with matter.
Everything from the size of atoms to how they bind.
Right. It dictates the size of atoms, how atoms bind together to form molecules, the colors of light they emit, everything. If this number were even slightly different, stars wouldn't burn the way they do, chemistry wouldn't work, and life wouldn't exist. Am I overstating that?
You are not overstating it at all. But here is the critical issue standard physics has with the fine structure constant. We have absolutely no idea why it is exactly that number.
We don't know where it comes from.
Not at all. Classical physics cannot derive it. We just observe the universe, measure the interaction, get 1 over 137, shrug our shoulders, and plug it into our equations to make them work.
That's hilarious, actually.
Richard Feynman, one of the greatest physicists of the 20th century, famously called it a magic number that comes to us with no understanding, and suggested that the hand of God wrote that number, and we don't know how he pushed his pencil.
But the Osmakani model just pushed the pencil. It didn't just measure the fine structure constant out in the world, it fundamentally derived it.
Yeah.
It organically generated a number that mirrors the fine structure constant purely from the raw masses of the proton and electron interacting with the new Gim constant.
Exactly. It completely changes the paradigm. It suggests that the fine structure constant isn't an arbitrary magical parameter forced onto the universe.
Yeah.
It exists as that specific number because of the precise relational balance between the mass of the proton and the electron within the triple equilibrium structure.
That is mind-blowing, but I want to push back a little here.
Please do.
Is it possible this is just a numerological trick? Like, If you play with enough constants and divide enough numbers, eventually you'll stumble into a number that looks like 1 over 137. How do we know this equation actually reflects reality and isn't just mathematical coincidence?
That is a highly necessary critique, and the authors actually anticipate that skepticism. Once they derive that coupling constant naturally, they show that other foundational atomic structures, like the Bohr radius, which defines the typical distance between the nucleus and the electron, and the Compton wavelengths, they all flow naturally from this math.
Okay, so it predicts other things too.
Yes, but the real proof comes when they change the particles. They test the equation on another pair, the proton and the neutron.
Okay, so moving from the electron cloud orbiting the nucleus to the particles crammed tightly together inside the nucleus itself. What happens when you plug a proton and a neutron into the coupling equation?
When you calculate the proton-neutron coupling, substituting the electron's mass for the neutron's mass, the math yields a significantly larger value than the atomic coupling.
Which perfectly aligns with experimental reality. Protons and neutrons are bound together by the strong nuclear force, which operates at incredibly short ranges, but is vastly stronger than the electromagnetic force holding the electron in its orbit.
Exactly.
The Osmakani model organically reflects that massive difference in physical reality just by swapping out the masses in the equation.
Yes. The relational structure automatically adjusts the strength of the coupling based on the specific masses involved. It demonstrates a stunning level of internal dimensional consistency. The math isn't just producing a random number, it's dynamically mapping the known hierarchy of forces in the universe.
Wow. Okay, let's shift gears and talk about movement. If mass, space, and time are locked in this rigid relational equilibrium, how does anything actually move through space?
Fine question.
If I throw a baseball, how does this relational thread account for velocity without breaking the equilibrium?
The paper addresses this by introducing the concept of Osmakani velocity. It posits that orbital or relational velocity emerges directly from the strength of the mass coupling we just discussed. The equation provided is velocity equals gm times the masses, divided by h bar. However...
There's a however.
Yes. The authors immediately include a major caveat here, which speaks to the exploratory nature of the work.
Let me guess. The math breaks when things go too fast.
Essentially, yes. They acknowledge that this foundational velocity equation works fine at classical normal scales. But as a system approaches the speed of light, this simple equation would require significant relativistic corrections.
Okay.
If left uncorrected, the math might theoretically allow for velocities exceeding the speed of light, which violates every known law of causality.
So they're openly admitting, hey, this is version 1.0. The core engine works for basic coupling, but we haven't built the relativistic speed limiters into the code yet.
That's a great way to summarize it.
I actually appreciate that. It shows they aren't claiming to have formulated a theory of everything overnight. They are mapping the domains where the framework holds up and explicitly pointing out where future physicists need to extend it.
It's the hallmark of robust theoretical work. They're checking their own dimensional consistency and inviting collaboration to refine the edges.
All right, I want to tackle the final major concept in the paper. And honestly, it's the phrase that sounds the most like pure science fiction to me.
I think I know which one you mean.
Yeah, but from what I read, it's a purely mathematical concept. The paper introduces something called Osmakani entanglement mass. We need to unpack this carefully.
Yes, we do.
Because in standard physics, entanglement is that spooky action at a distance Einstein hated, where two quantum particles are linked, and affecting one instantly affects the other no matter how far apart they are. What does it mean for that entanglement to actually have a mass?
Well, you have to detach from the traditional quantum definition of entanglement for a moment.
Yeah, detach.
In the Osmakani framework, entanglement isn't just about instantaneous communication between two distant particles. Here, Osmakani entanglement, mass denoted as μ, is defined as the effective measure of internal relational coupling between particles.
Let's put that in plain English. Effective measure of internal relational coupling. Does that basically mean how densely woven the relational structure is within a given system?
Think of it as a metric of structural density, yeah. The equation for it is μ equals m divided by alpha O.
Okay.
So the entanglement mass is the actual mass of the system divided by the dimensionless coupling constant we just spent time dissecting.
Okay, so it's a ratio of mass to coupling strength. How tightly the thread is pulled between the mass, space, and time.
That's a good way to visualize it. And by running this equation, the paper derives specific structural limits. a minimum entanglement limit, which happens to be based on the mass of the proton, and a maximum entanglement limit based on the mass of the electron.
Interesting.
But applying this math reveals a deeply counterintuitive paradox.
Hit me. I love a good physics paradox.
The relations indicate that larger actual masses correspond to more compressed entanglement structures. Conversely, smaller actual masses correspond to more extended relational structures.
Wait, I'm struggling with that concept. My intuition says bigger mass, bigger structure. Like a bowling ball takes up more space than a marble. Why would a larger mass have a more compressed entanglement structure?
That sounds backwards.
Completely backwards. Let me try to build an analogy to see if I grasp the mechanics of what you're saying. Imagine a coiled spring.
Okay, a spring.
A really massive object is like a heavily compressed, tightly wound industrial spring. The actual mass is high, but the internal relational structure, the coils, are incredibly dense, tight, and confined to a small area. The entanglement is compressed.
Right.
But a lighter object, the smaller mass, is like a highly stretched out, loose rubber band. The actual mass is low, but the relational structure extends much further out into space because there isn't as much mass anchoring it tightly to a localized point. Does that track?
That analogy tracks perfectly with the mathematics of the model. The heavy mass compresses the relational web. The light mass allows a relational web to cast a wider net.
Wow.
It flips our classical intuition on its head. And this paradox directly leads to the final brilliant synthesis in the paper tying this entanglement mass directly to the concept of energy.
Energy, the ultimate currency of physics. How does energy fit into a compressed spring or a loose rubber band?
The model introduces one final culminating equation, EO equals mO times c squared.
Wait a minute.
Osmakani energy equals the Osmakani entanglement mass multiplied by the speed of light squared.
That looks awfully familiar.
Yeah.
That is Einstein's iconic E equals mc squared, but the traditional mass variable has been swapped out for the entanglement mass variable.
Exactly. But the philosophical implication of that swap is staggering.
How?
In Einstein's equation, energy is essentially a property of the object itself. Mass and energy are interchangeable states of an isolated thing. But in the Osmakani equation, the potential energy of a physical system is directly tied to the relational structure of the participating particles.
So energy isn't a property of an isolated object floating in a void. Energy is a property of the relationship between the object, space, and time.
Yes. If you alter the entanglement, if you compress the spring by adding mass or stretch the rubber band by removing it, you alter the fundamental energy of the entire system, because energy is stored in the structural tension of the relationships, not just in the objects themselves.
Man, okay, let's step back and look at the massive journey we've just taken.
It's been a journey.
We started this deep dive looking at a broken bridge. Two brilliantly accurate yet totally disconnected maps of reality. The smooth macro geometry of general relativity and the pixelated jumping micro world of quantum mechanics.
The Great Divide.
Right. We explored how the Osmakani model attempts to build the missing stairs by refusing to treat mass, space, and time as separate entities. Instead, it uses a triple equilibrium to tie them together as one dynamic fabric.
And introduces new math to prove it.
Exactly. We discovered a new universal constant, GM, which acts as the massive structural glue of this fabric. We saw how this framework incredibly derives the fine structure constant organically, stripping away its magical status. And finally, we saw how mass dictates the compression of these relational structures, redefining energy itself as a property of entanglement.
It is a remarkable theoretical exploration.
Yeah.
And we must reiterate, this is the foundational stage. It is a mathematical scaffolding checking its own internal consistency.
Sure.
But the groundwork it lays is undeniable, paving the way for future physics to potentially unite our disjointed maps of reality once and for all.
It really makes you rethink the fundamental nature of the reality you walk through every day. And I want to leave you, the listener, with a final thought to mull over today, building on the implications of this model.
I'd like to hear.
If the Osmakani framework is pointing in the right direction, if mass, space, and time are truly not independent entities, but just interconnected components of a relative equilibrium, and if energy itself is fundamentally a property of structural entanglement, what if the universe isn't a collection of things sitting inside an empty box of space?
Oh, that's deep.
What if it is an infinitely complex web of pure relationships? If you were to somehow miraculously sever all the relationships, all the couplings, all the mathematical ratios between objects, does the physical world even exist at all? Or is the connection itself the only thing that is truly real?
That's something to think about.
Next time you look at that duck-rabbit illusion, ask yourself, maybe the reality isn't the duck and it isn't the rabbit. Maybe the only reality is the lines connecting them. Thank you so much for taking this deep dive into the absolute foundations of our universe today. We'll catch you next time.